Hi there, for those of you watching the recording. Um, Before I actually jump into this, I did want to mention that there was no lecture on Monday, so no need to ask about that. Unfortunately, I was not able to make it because I got my second COVID shot and I've been under the weather. I'm still not doing great today, but we're going to try to to soldier through so that y'all can take your midterm, and we'll see how that goes. In terms of the work that's due this week, I am going to cancel the lab for this week, and so you'll just have your proofs, which is the practice midterm, I believe. So let me check in here. Yeah, so there's web work and the practice midterm, and that'll be all you have to do this week. And the practice midterm is going to be all considered to be collaborative proofs. So for that practice midterm, you want to post all your solutions. Yeah, thanks, Natasha. Yeah, yeah, the first one was fine, no effect at all. And now I've been out for like going on 3 days now. It's not great. Okay, so here's the practice midterm. So you put your responses to that just as you would for a collaborative proof right into this discussion forum. And so there will not be a proof this week either in the sense of a graded proof. There'll just be a bunch of collaborative proofs. And for those of you that had me before, this is the same thing that we did last term. But for those that are new, there won't be a proof or a lab this week. There'll just be a bunch of collaborative proofs that are designed to get you in shape for the midterm. So I'll talk more about the practice midterm in a minute, but that's just what's going to be due and what I've canceled. Does anyone have questions about that? The midterm itself is going to be Saturday to Tuesday next week. I haven't decided whether I'm going to have it be timed or not. I think last year I had it not timed. So you could just use the entire duration of like 3 days to work on it. But I haven't decided yet. Do people have a preference on whether they'd rather have a timed exam that's easier or a not timed exam that's harder? Does anyone have any opinions there? That's right, Haruka. The lab's canceled. The collaborative proofs are the practice midterm, and there's no graded proof. Uh, Untimed. Your second shot's on Friday. Okay, not timed, not timed, not timed. Okay, so saying, does anyone want it to be timed? Let me ask the reverse question here. Cool with whatever. Okay. Well, it sounds like people are timed would definitely be easier. Yeah, because you'd have a tenth as much time. So okay, well, Sean and David want it to be timed, but you guys are you're some of the people that answer most of the questions in here too. So that being said, let's have a vote. Um, so if you would find in your participants window or possibly in some other window, I forget where they are, but there's a yes and a no button, a green check mark yes and a red X no. Um, for me, they're in participants. Um, uh, Tamara, so but before we vote, when I say timed, you can do it whenever you want, but you only have 3 hours to work on it, right? So it's not at a specific time. It's just that it's a limited time. Does that make sense? Yeah. Okay. Cool. Yeah, because we're gonna have lecture next week. Like we gotta keep moving forward. So we're not gonna take class time to do this. Um, so okay. So that being said, I think there's like reactions is like another tab that some people have here in Zoom, and it might be under there as I recall. Um, but if everyone could click the little yes and no buttons, yes for, let's say yes for untimed and no for timed. You just don't want to spend more than 3 hours on it. Sure, I understand that. There's pros and cons. Okay, so if I've got 3 yeses for untimed, I've got nobody for timed. Okay, 4-1. We have 17 people here and only 5 have voted. So faster we do this, the faster we can get through more material and make sure that y'all pass your midterm. So if you're going to vote, do it in the next 10 seconds, please. Otherwise, I'll assume that no one else cares. You're neutral. That's fine. Neutral's good. Yeah, okay. Yep. On time means no time limit. That's correct, Haruka. It'll be a harder exam with no time limit or an easier exam with a time limit, right? Someone switched from yes to no. Oh, goodness. Okay, well now, okay, so now people want it to be timed. Okay, so now it's 4-3. Is everyone voted? Who cares? Oh yeah, sorry. I probably I blew through that. The easier one will be timed. It has to be because you don't have as much time to work on it. You have 3 hours instead of 3 days, right? I mean, I guess the other one's timed, but it's just the time is 3 days. So okay, well, no one else cares. Okay, it's 4-3, so it'll be timed, right? So I'm going to take the exam that I have and make it a little bit easier so that you can complete it in 3 hours. Okay, cool. So that's fine. Your midterm will be open from Saturday at midnight, so Sunday morning, to Tuesday night. And during that time, you're going to take 3 hours at some point to complete the exam. And let's see, the way that I'll distribute it, does yes, the practice midterm would be a little bit harder because the practice midterm was an untimed exam. It was like a take-home exam, right? Back in the before time when we went on campus, right? And we had take-home tests versus in-class tests. This was a take-home test, so it's like a 3-day test. So the practice midterm will be a little bit harder than the real midterm would be. Yeah. Okay. The way that I will distribute these things is that I'm going to have to do what I did last term and make a quiz, because right now it's set up to be untimed. So here, let me show you. Well, I can't show you because I haven't made it yet. But in order to find your midterm, there's a Dropbox right now that has your midterm in it, and I'm going to get rid of that and change it over to a quiz instead. And so, when you open up that quiz, then you'll be able to, it'll be timed for 3 hours, and all the questions will be listed there. And then your answers, you can just put back into the quiz. Yeah, Brian, I'll definitely do that. Would you shoot me an email to remind me, Brian? That'd be great. Thanks. So Haruka, the timed one is easier because it's shorter, right? You can't do as much work, so the work that you're doing can't be as complicated, right? So it's easier. Does that make sense, Haruka? Okay, cool, great. So as I was saying, there will be a quiz. You'll go into the quiz, and you'll find the questions there. When you get all your answers done make a Microsoft Word document, or you have photos or PDF or whatever you have, you can just upload those files back into the quiz, and that's where I'll find your responses. So I will be getting rid of the Dropbox there, and the whole thing will just be a quiz. Is everyone good on that? Does that make sense? It'll be kind of a weird quiz in that you don't like write anything down in it. You're just going to attach, the same way that you do your graded proofs or your collab proofs, however you do that, whatever, you've been doing that's comfortable for you, just do it that way. Just attach, files to the quiz for your answers. Just like the one last semester. Yep. Mm-hmm. I keep putting down fluids. Okay, cool. So great. So that's the midterm. So you've got the practice midterm is all you have to do this week, and the web work. The practice midterm and the web work are all you have to do this week. And then the midterm starts when those are due, Saturday night. And then the midterm starts. you'll have 3 days to finish that up. And it'll be a quiz where you put your answers and responses into that quiz. Cool. So that's the business for this week. And again, my apologies on missing Monday, but yeah, I was even here. I think some of you saw me. I was in the room and I was like, oh, I can do it. I can do it. And then I was like, oh, I can't do it. so my apologies there, but we're going to make it through today. And I'm sorry if I'm rambling because my head is all messed up, but yeah. I mean, I'm not destroyed. I mean, you can hear I'm still viable. It's just, yeah, it's just a little sore and my brain's not working very well. But yeah, right afterwards was unpleasant. Okay, so let's do some math, right? This is gonna be great. So we'll do this one and then we'll get into the practice midterm for Alakai. Luckily, Alakai got me in the mood here today because we were talking about the practice midterm for a half hour before class. So at least my brain is in math land at this point. So that's good. Okay, so here's our problem. We've got 5 cards simultaneously drawn from a standard deck of 52. What's the probability that at least 3 of the cards are aces? Okay, so what's going to happen here is there's a number of different things that could happen. Okay, you could draw 3 aces or you could draw 4 aces. In that case, what do you do to those probabilities to combine them? If you have this thing could happen or this thing could happen, you add them. Good. That's the addition rule. If you have an and, right, like 3 cards are aces and 4 cards are well, let's say 2 cards are aces and 2 cards are queens, something like that. That would be an and that one you would multiply, right? But here I have an or, right? So we'll be adding. So we need to find 2 probabilities and add them together. We need to find the probability that exactly 3 of the cards are aces and the probability that 4 of the cards are aces, and then we'll add those together. That'll be our answer, right? So let's go through each one in turn. So what is the probability that 3 of the cards are aces, right? So how would we figure that out? What do you guys think? How many ways to choose 3 aces? Okay, good. So how many ways would that be? 4 choose 3, good, right? Because we have 4 things to choose from and we're choosing 3 of them. And what is 4 choose 3 equal to? 4, good. And I think a nice way to think about that is rather than 4 choose 3, you can think about 4 choose 1, because each, for any of the 3 aces that you choose, the converse way of looking at it, or the complementary way of looking at it, is that you're excluding one of the aces, right? So you can think about, oh, well, how many ways can I pick them? Well, that's, I could exclude each of the 4 aces. So there's 4 ways, right? And we're going to talk a little bit later today, once we get into the binomial theorem, about why 4 choose 3 is equal to 4 choose 1. So we'll discuss that a little bit later. Then Haruka, you've got a nice response there, which is you have 4 choose 3, which is how many ways are there to pick the aces, and multiply, you have to pick the remaining 2 cards for your 5-card hand, right? Which is 48 choose 2, because you can't pick any of the aces. So you would have 52 minus the number of aces, so minus 4, which is 48. And then of those 48, you're choosing 2 of them. And Haruka, you're saying 48 choose 2 is 1128. Let me just check that. I don't know if that's true. Let's double check. 48 choose 2. 1128. Yep, that's right. So we would have 4 times that as the number, the number of ways we could get 3 aces in a hand. So we're going to have 4 times 1128. Okay. And the probability of that happening, well, maybe we shouldn't here, but yeah, we need to divide by the space size. So what are we dividing by here? Yeah, 52, choose 5. Very good. Yep. So let's see what that is. 52, choose 5. All right, and I'll just pop this guy over here. Did that work? There we go. All right, divided by this thing. Okay, I'm just going to parenthesize this for a moment. Okay. We still need to account for the 4 ace hand. Absolutely, Sean, that's right. And what I'm going to do is in my numerator, I'm going to add on the 4 ace hand, right? Because that's the other way that I could successfully get a hand where at least 3 of the cards are aces with that or that I was talking about, the addition rule, right? So I'm going to take the 3 ace hands or the 4 ace hands and then divide that by the sample space size to get the probability. Is everyone with me so far? Any questions on all of that? Okay, very good. So the 4 ace hand, you have to pick all 4 aces. So there's no choice there at all. The only thing that you get to pick is the one remaining card, of which there would be 48 choices because you've already got all the aces. 52 minus 4 is 48, right? So that would be plus 48 divided by this guy. And let's see what we got here. Oh, and it hates it. Uh-oh. Well, let's see what it's supposed to be. No, we have a different answer, right? You can see there's our 0.0017. This is 0.0019, right? So, yeah, so we made some kind of mistake. So what would our mistake be? So Haruka, I think your method was good. It could be an issue with the problem unless someone sees a mistake that we made. I'm going to need your guys' help today because my brain is not great. It looks like we got the right answer to me, but does anyone see any error that we may have made? Okay, I'm going to take that as a no. So I'll go back and look at this problem later. So Haruka, would you shoot me an email about this problem? And I'll probably, so what I'm doing on these, there's been a couple of problems, and that whole section that was broken from what, 2 weeks ago. I'm just going to not count those questions in your final grade at the end. That's all. So I'll either fix this one, but I probably won't because I'm not going to have time. So I'll just remove this from the items that you're being graded on, because I think that we did do it correctly. Yeah, I think it's broken. I'll think about it a little more. If I do figure it out and we did it wrong, I'll shoot you all out an email and let you know. But yeah, I think this one's probably broken. Think about it. Okay, in that case, let's move on. So next, Alakai wanted to talk about the practice midterm, and I'm happy to talk about that at length. The ones that we hadn't gone over yet were questions 4 and 5. And so I'm happy to do those. And then if anyone wants to talk about 1, 2, or 3, we can talk about those as well if people need help on that, because I'm happy to help here. So here's what we've got. We have a lecture hall of 50 students and an evil math professor who makes a bet against the students. He bets that at least 2 students share a birthday and that the odds of this happening are 49 out of 365, since each student is in the same situation of getting 49 chances to match a birthday out of the total 365 birthdays. He even gives 2-to-1 odds, right? Even though it's 8-to-1 winning to win, he even gives 2-to-1 odds, offering $2 to every student if he's wrong, but he'll only take $1 from each student if he's right. Yeah. So bear in mind, he's an evil math professor. And so for that reason, right, there's something false. There's something, there's a lie in the way that he describes this situation with the birthdays, right? So assuming that having one birthday is just as likely as any other, what is the actual probability that two students in this class share a birthday, right? So the professor said it's 49 out of 365, but that's not true, right? So what do you guys think? What's the actual probability that two students share a birthday? How could we compute that? No ideas? How should we start to pick things and count things? It is more like 97%. That's true. The sample space is 365 squared. Okay, why is that? So how did you guys get both of those things?
So I just typed in birthday paradox calculator, and there's a bunch of those online that you can go check out and put in the right numbers, and it comes out as about 97%. I forget how this problem goes, but it's a pretty famous one, the birthday paradox.
Yep, it certainly is. Birthday problem, birthday paradox, same thing. Okay, so here's the probability, right? That in a set of n randomly chosen people, some pair of them will have the same birthday, that's the bet, right? And it turns out to be 50-50 at 23 people, right? So you only need 23 people for there to be 50-50 odds that two people in the group have the same birthday. If we have 50 people in the group, you can look right here, 50 people gives you about a 95, and you said, Sean, 97%. So somewhere in there, 95, 97% probability that two people share the same birthday, right? And that's when birthdays are evenly distributed, but we'll make that assumption. We'll assume that birthdays are evenly distributed. Yeah, okay, so Haruka, you have an interesting little formula there. How did you come up with that? Okay. For there to be none of the same birthday, so Lucas, that's great. That's a great move. Instead of saying who does have the same birthday, we'll see who doesn't have the same birthday and subtract it off, right? Oh, and Haruka, I guess that's what you were saying, right? Because that's why you have the subtraction there. Okay, perfect. So it's the total number minus all the remaining possibilities, right? Which would be, the first student has 365 possibilities. The second one has 364, then 363. So you can see here, right? This is our little equation for the probability of A prime. A prime in this case is that people don't have the same birthday. The prime is supposed to be like a negation, right? Where does it define A prime? There we go. It's simpler to calculate the probability of A prime, the probability that no one has the same birthday, right? So he's making a bet that people do have the same birthday. And here we're saying, oh, well, instead we'll look at that no one has the same birthday. And the reason why is because otherwise you need to compute the probability that two people have the same birthday, or three people do, or four people do, or five people, all the way up to the probability that all 50 people have the same birthday, which is very unlikely, but still possible, right? So to avoid all that, we'll calculate the what I've been calling the complement or the converse, right? Which is that no one has the same birthday. And we'll subtract that off of 1, right? So we get P of A equals 1 minus P of A prime. That's that subtraction rule that we were talking about. And to do that, I think we've got the right idea here. So we'll add up 365 to the 50th, right? Those are all the denominators. Sorry, not add up, multiply. And we'll get 365 to the 50th in the denominator. In the numerator, we'll get 365, 364 multiplied all the way down to, as Haruka said, 315, which is 50 less, right? And then it's going to be 1 minus that whole thing, right? So if we do that, so let's calculate it. So we'll have 1 minus, oh, I guess I do have to be careful here. So I want 365 factorial divided by, if Google does factorial, so I guess we're going to find out 315 factorial or 314 factorial. Oh, and that's also going to be divided by 365 to the 50th. Right? Is everybody happy with that? Oh, 316. Did I do it the wrong way? Well, no, because then we're removing. I think then we're removing. I guess, I mean, it doesn't matter much, but here, I think let's do it this way. And it's not going to be factorial. Ugh. Okay. Okay, yeah, that's fair, Lucas. Yeah, you could use Python. I was hoping to do oh, I didn't have a closing parenthesis. Wait, let's try that. No, still doesn't work. Okay. If we actually do this out, let's go on Desmos. Scientific calculator should be fine. And then let's grab this guy. And it will not do that either. Does anyone have well, we can just trust Lucas. I think that's a good way of doing it. And Lucas, what did you get as your result? Okay, you did get 0.97. Okay, so we'll round. We'll say it's a 97% probability in a classroom of 50 students that at least 2 students share the same birthday. Right? Thanks for that. Appreciate it. Okay, so the actual probability, instead of 13.4%, it's actually 97%. So that's why the professor is evil, because he said, oh, it's only 13% probability, but it's not, it's 97%. So he's cheating the students out of money, right? So part 2, and actually we are not going to get this far. What's the expected value of the bet to the professor? What's the expected value to the student? Now this part we haven't gotten to, and we won't get to it before the midterm either. That's section 9.8. So we actually won't be doing expected value, but I can quickly explain what it means. The expected value is the likelihood that something will happen multiplied by the amount of money that you get if it does happen. And what you do is you take all the different things that could happen with all of their probabilities, and you take each one of those things that could happen with its probability, multiply it by how much money you get in case that happens, and then add up the results. So it's basically, it's a big summation, and inside the sum, right, you're adding together a bunch of probabilities multiplied by how much money you get if they happen. Does that make sense to people? Maybe I should do an example, right? Or we can do this as an example. This will be fine. So the expected value of the bet to the professor, okay, is going to be, there are 2 possible outcomes. Could be that the professor wins the bet, or it could be that the students win the bet, right? So in the case that the professor wins the bet, what's going to be the expected value? Well, it's the probability that he's going to win, which is 97%, so 0.97, right? Times the amount of money that he'll get, which is $50, right? He'll only collect $1 from each student, so 50 students means $50, right? So the expected value to the professor is 0.97 times $50. Okay. But that's only one thing that could happen. The other thing that could happen is the professor loses the bet. And what would happen there? Well, that would be 0.03, because a 3% chance that it'll lose, times $100. And that would be subtracted from the first one, right? Because that would be the first outcome would be a gain for the professor, and the second outcome will be a loss to the professor. I'm sorry, there's a fly in here that my dog is hunting. Okay, she stopped. Sorry about that. So dog life, right? Okay, so are people okay on that idea? Does that idea make sense? Yes, cool. Okay, so let me ask you guys this. What would be the expected value to a student? Good. So you're close, Sean, but you have the decimal points. There we go. So it would be $2 times 0.3. It would be actually 0.03, right? So that first decimal point needs to scooch over as well. So it'd be $2 times 0.03 minus $1 times 0.97. Yes, that's exactly right, Haruka. Yep, and that's what Sean meant. Good. Okay. And so we can actually calculate those out if you want, but basically the professor makes a bunch of money and the students, each one loses a little bit of money. The expected value is what you would, it's sort of like an average, right? It's like if this happened like millions of times and you took like the total amount of money, let's say that the professor is he's very old. Okay, a lot of old evil math professors, right? He's a wizard, and so if he did this, he taught this class 1,000,000 times. Okay, and each of those times he either won or lost, right? If you at the end of those million terms, you added up all the money that he made and divided by 1,000,000 to get an average of how much he made per class, that would be the expected value, right? So it's what you expect to make. Now, you're not actually going to make that. You're either going to win or lose, which is totally different than the expected value, right? So it's not what you're going to get. It's what you would expect to get if you were to repeat the bet over and over and over and divide by the total. It's like the average value that you'd get per bet. Does that make sense to people? Is that good? Normal distribution. Not exactly. So maybe what you're referencing is the law of large numbers. Is that maybe what you're thinking about? A normal distribution is a little different. Okay, fair enough. No, so it is not a normal distribution, but it is the law of large numbers, which says that if you repeat something for a lot of times, a large number of times, then the chances that you'll deviate from the average reply, or the average amount of money that you make from the bet in this case, the chances that you'll diverge from that average get smaller and smaller and smaller the more times that you make the bet. So you sort of think of it as like a limit of a sequence, right? As you approach the limit, you're going to, in doing this bet over and over and over, and divide by how many times you've done it, then you'll come out with this kind of average, which is adding up all of the probabilities multiplied by the value to the better, right? Any questions? Makes sense. Okay. So that was a bit of a diversion. We're going to talk a lot more about that next week and do a bunch of examples. But I think from there we should move on because we do have a lot to cover today. Let's talk about number 5. Okay. A is a non-empty set. I want to prove or disprove that the number of subsets of A whose size is even is equal to the number of subsets of A whose size is odd. And here's an example. Let's say that A equals the set 1, 2. Here are the subsets of A: empty, 1, 2, and 1, 2. And since there are two subsets of odd size, those are the singleton sets, two subsets of even size, that's empty and the full set. So this has 0 elements for its size, and this has 2 elements for its size, both even numbers. The claim is true for this example, because this is even and this is even, right? I'm sorry, I said that wrong. The number of even ones is equal to the number of odd ones, right? So here's the odd ones, and there's 2 of them. And here's the even ones, so it's equal to that because there's 2 of those also. Okay, so what do you guys think? How could we go about proving this? Recurrence relation, okay. What would that be like, David? For evens and odds, can you say more? Okay, so for size n, make a recurrence relation for evens and a separate one for odds. Okay, that makes sense. Let me rephrase that a little bit. I think I see what you're saying now. I think what you're talking about is an induction proof. Is that right? So we say, you know, we have this, yeah, okay, good. So we have this example where it works. So I've given you a base case already, right? So if you want to go the route of an induction proof, the base case is already there for you, right? It's described right here. From there, what would be our induction step? What are we inducting on? What's sort of the n and what's the n plus 1? What are we adding on to is my question. See if it's true for size n plus 1, good. And if the size is n plus 1, that means that we're going to throw in another number. So we started out with a equal to 1, 2. And what we want to do is say, okay, well, if we add the number 3 to a, what's going to happen to the subsets, right? Okay, well, if we have a third item, there are 2 things that could happen to the subsets that we already have, right? What might happen?
So this is, I'm thinking, so right here we have 4, because we have 2 things, right? 2 squared is 4. It's an even number, so you can have odds and evens be equal, right? But if you had a third, my intuition wants me to say that it'd be 3 squared, and you or
2 cubed.
Is it 2 cubed?
Yeah, it's
okay,
2
then it'd still be even then. See, I was thinking like if you end up with 9 total things, then it can't be possible because then
you're right if that was true, but it's not.
Okay, then never mind. I have no clue then.
Yeah, so this is the number of subsets of A, which is this, that's what the power set is, right? So really what I'm asking about is about dividing up the power set into the even size sets and the odd size sets. Does that make sense?
Yeah, yes.
Got it. Okay, cool. So David, you said it holds or it doesn't. That's not quite what I was going for. So what I'm saying is when we have the subsets of A, which is just the set 1, 2, then we add in a third item. What happens to these subsets when we add that third item? There's 2 things that could happen to them.
The subsets change or they stay the same?
Very good, right? They either get the third item added or they don't, right? Now think about what happens in each of those cases. If we don't add the third item, we just have these 4 things again, right? And if we were in this situation, the number of even things is equal to the number of odd things, right? We got 2 and 2. What if we do add the third item to each of these 4 sets? What happens then?
then everything that was odd is now even, and everything that was even is now odd.
Which makes it still equal, right? Perfect. That's exactly right. So we have the original 4, where the number of even things equals the number of odd things. We have the new ones with the third item added, where the number of even things equals the number of odd things. And to get the total, we just add them together. So of course, in the total, the number of even things equals the number of odd things. There you go. That's your induction proof. I'm talking through it to save time, but I can write it out if people have no idea what the heck I'm talking about. Thoughts? Seems good to you. Made sense? Okay, excellent. Okay, cool. So in that case, let me just say there's another way to think about it as well. You can also add up all of, you could take a, you know, a set of arbitrary size and add up all the even size sets and add up all the odd size sets and show that they're equal. And there's no induction there at all. It's a counting proof, right? And you can do it that way as well. And once we do choose notation, maybe someone remind me, we'll go back and use choose notation to prove it that other way, right? We just don't have that, we don't have that tool quite in our toolbox yet. But when we do, I'll circle back and talk about it. But before we do that, let me look at numbers 1, 2, and 3. And I can either, I could do one of these in detail, or I could sort of talk about them loosely, or we can just move on. What do you guys like to do here? Maybe we should move on. Is there anything that in particular anyone's like super confused by? The 16 relations. Okay, happy to talk about that. So there's a set S that has AB in it, and a relation over the set means a relation from S to itself, right? So the possible items that could be in the relation are the elements of S cross S, because the relation is going from the set to itself, right? So the possible items in S cross S are as follows: AA, AB, BA, BB. Sorry, it's hard to type this. Okay, those are the possible pairs that may or may not be included in the relation. Since each of 4 items may or may not be included, the total number of relations is 2 to the 4th, because we have 2 choices. They're either in or they're not for 4 items. So 2 to the 4th, 16 possible relations. So as an example relation, maybe you just have, you know, these 3 guys. This would be one of the possible 16 relations right here, right? Or as another one, maybe for another possible relation, you just have the pair AA, and that's your whole relation. So there's 2 out of the 16 possible relations. For each one, you say whether it's reflexive, symmetric, or transitive, right? So you'll have, you know, 48 answers there. Does that make sense? 3 answers for each of 16 possible relations. But they should go quick. I mean, this one is supposed to be easy. Well, easier than the rest of them anyway. And Kobe, that makes sense. Okay, great. Any other questions on this one? Great. Okay, cool. So in that case, let me stop share. Let's turn on the video here. There we are. Okay, cool. So number 1, part 2. Sure. Let me switch back. Okay, number 1, part 2. what's the probability that the symmetric difference of 3 randomly chosen elements in the power set is the empty set? Okay, so the idea here is that you have a power set of a set. You're picking 3 elements from it. So you're picking 3 subsets of S. You're going to take the symmetric difference of them all together and see whether or not that thing is the empty set. Now, there's a really important way of looking at this that I can tell you as a hint, okay? Rather than thinking about choosing 3 randomly chosen elements in a power set, let's think about 2 items, 2 sets being symmetric difference together. How do those sets have to be chosen so that the symmetric difference is the empty set? Okay, so I'm just symmetric differencing 2 sets. What property do they have so that the answer of the symmetric difference turns out to be the empty set? It has something to do with the intersection, kind of. Not mutually disjoint. They have to be the same set. Yeah, so Sean, you had you had it reversed, right? So the symmetric difference is sort of like exclusive or, right? It's one or the other, but not both, right? So to get there to be nothing that comes out, that means that they must have had everything in common, right? If they had nothing in common, which would be mutually disjoint, then everything would be in the symmetric difference. But we want an empty set for this, so we want nothing in the symmetric difference, which means the 2 original sets coming in have to be exactly the same, right? Is everybody happy with that so far? Any questions there? Okay. Now, in that case, let's say now that we randomly choose 3 sets out of a power set, what has to happen, just in English, like how should we think about, okay, you'd have to choose the same element from the power set 3 times. Okay, Sean, you're really close, but that's not quite right. You're on the right track. It's not that all 3 of them have to be the same. What has to be the same? Two of the 3 of them have to be the same and contain the third. Now, it's easier than that. Just 2 of 3. Not exactly. Not quite. Again, that's true, Lucas, but there's more than that. Okay, so if we have 2 of them the same and the third is empty, that will give us an empty total when we do all 3, because when we do the first 2, those will be the same, and so the answer will be empty. Then when we symmetric difference with the third one, we'll have empty, symmetric, empty, and those 2 things are the same. Empty and empty are the same as each other, so the whole result would turn out empty. So that would work, but there's more possibilities. And David, 3 are the same is not quite right either. It's a little more complicated than that. What you want at the end of the day, what you want at the last minute before you finish this problem, is you want to be taking 2 sets that are the same and symmetric differencing them together. What that means is that this set and this set have to be equal, right? The third set has to equal the symmetric difference of the first 2 sets, so that when you take this final symmetric difference right here, the result pops out to be empty. Does that make sense? So it's not that all 3 are the same or that 2 out of 3 are the same. It's that the answer from the first 2 is the same as the third one, right? So what does that mean for the probability? Because I want the probability that the symmetric difference is the empty set. So what's the probability that the symmetric difference of the first two sets equals the third one? How could we think about that? Any ideas? Beautiful. That's exactly right. The first two can be anything. Okay. So these guys, when you symmetric difference them, you could get out whatever result you want, as long as the third one is the same as the first two, right? So for the first two, you can pick anything. For the third one, how many choices do you have? Just one. Yep, perfect. Yep, just one, right? Whatever this answer is, that's the thing that you have to choose for C, right? So what's the probability? Well, that's going to be, well, you can pick anything you want here, anything you want here, but this one, you have a 1 in the size of the power set chance of picking exactly the right thing for C so that it's equal to A triangle B, right? And that chance is 1 out of 1 over 2 to the n, because the size of the power set, as I've said here to remind you, size of the power set is 2 to the n, right? Questions? Okay, cool. So actually, let's do this. Since I've gone over all this stuff for a while, and we're almost in an hour, I'm going to take a short break. Let's take 5. I'm going to refill my water and chill for a sec, and we'll come back and we'll jump into section 9.4. So for the next 5, you think about if you have any questions on this or any other things that we need to do, and then we'll jump back into the book material when I return. See you soon. All right. Hey there, everybody. Anyone think of any questions for me? All right, cool. Let me start recording and we'll jump in here. Oh, we are still recording. Uh-oh. Okay. I thought I paused the recording, but I guess I didn't. Oh, yeah, it says recording. Okay. Well, for those watching the recording, sorry you had to wait. My bad. I thought I paused it. Okay, so let's jump into section 9.4, which is a pretty straightforward section in terms of the basic concept here. So the basic concept involves what's called the pigeonhole principle. Can anyone explain what that is? If you want to hop on the microphone here, please feel free.
So the pigeonhole principle, as far as I understood it, was pretty simple. It's if you have, 10 holes and 11 things, something's going to have to double up if you're trying to put everything into a hole.
Perfect. Your microphone went a little wacky there at the end, but yeah, that's exactly the right idea. If you have 10 holes and 11 pigeons, you're trying to put pigeons into the pigeons live in holes where it's like their nest where they sleep, right? So you're trying to put the pigeons into their bed so they can go to sleep, okay? And you have 10 holes, but you have 11 pigeons. Well, then one of the pigeons is going to have to double up, right? It's as simple as that. If you have too many things for the containers that hold them, then you're going to have to put at least two things into one of the containers. And that's the pigeonhole principle, which sounds really simple. And it is pretty simple, to be honest. I think the problems here are a bit easier than a lot of the other ones we've been working on. So let's do an example, right? Let's say that we have 6 pairs of boots, so 12 total boots, thrown in a pile. We have 6 pairs of boots in a pile. How many boots do you have to pick out of the pile before you're guaranteed to find a pair of boots that's a match? Until a guaranteed match. Perfect, 7. GUA. Match 7. Good. And it's 7. Sean, you want to explain? Why is it 7?
So the worst case scenario is that you pick 6 different boots, but then you picked one from each pair, so the 7th one must match one of those.
Perfect. Yeah. So your mic sounds like it got fixed there at the end this time, so that's good. But you said it exactly right. Let me repeat it in case people weren't able to understand. There's the worst case scenario, which is that you pick 6 different boots because there's 6 pairs, right? So in the worst case, you pick 6 and you get 6 different ones. That's okay, Sean. No worries. Feel free to hop on again and we'll see if it's fixed next time. And then that 7th boot that you pick, that's gonna have to match one of the original 6, right? So here, the sort of the pigeonholes are incorrect boots, and the pigeons are boots, right? So you can sort of think about like which are the pigeons, which are the pigeonholes. Okay, so let's try another one, right? How many integers from the set 1, 2, 3 up to 2 to the n, 2 times n, pardon me, not 2 to the n, 2 times n, must be chosen until an even number is guaranteed to be in your selection? That's a 2 times then. Any ideas? It's pretty similar to the last problem. Now it's just a variable instead of a value. Okay, so perfect, n+1, great. So what's happening is that you have these 2n integers, right? So let's say n is 10, for example. Then this set would go from 1 up to 20, okay? So n is 10, we have integers from 1 to 20, and just like the last one that Sean said, the worst case scenario for choosing an even number is that you keep picking odds. So in the worst case scenario, you would pick 1, 3, 5, 7, and so forth, all the way up to 19, or in whatever order you want. So you never pick an even one for the first 10 numbers, because there are 10 odd numbers that you might choose. Only on the 11th one, n+1, as as Sean said in the chat, are you guaranteed to pick an even number? Any questions there? You just sort of keep thinking about worst case scenarios, right? Which is what happens with the pigeons, right? I mean, the whole idea comes from, the 1700s when they used to have pigeon carriers like Game of Thrones, right? For those of you that have seen that, right? They used to send little messages back and forth tied to pigeons' legs. And so there would be, people whose job it is to take care of all the pigeons, since those were like the telephone, basically, or, mail system. So the worst case scenario for the person in charge of the pigeons is that there are too many pigeons at home, right? Yeah, they're the earliest network engineers, right? So there's too many pigeons in the coop at once, and there's not enough holes for all the pigeons. And that's the worst case scenario for the pigeon handler, right? And so that same idea is what's happening here in terms of worst case scenarios, where the pigeon handler is choosing which hole to put the pigeon into. Here we're choosing which number to pick to pick out of this set. And the reason why it's such a goofy analogy is because the principle was invented when when everyone knew what pigeonholes are, right? It's hundreds of years ago. Any sort of early writing here, the analogies that are used are going to be anachronistic is not the right word. Old, right? Ancient, strange. Right. So let's try another one. And this one makes an attempt to be archaic. Thank you. That's the word I was looking for. Thanks, William. Thanks for helping me with my brain today. I need it. So this one tries to be more relevant, but it's still kind of goofy. So let's try one more. A programmer writes 500 lines of code in 17 days. 500 lines in 17 days. Oh, that's not a question. Okay. Must there have been a day with at least greater than or equal to 30 lines? So how do you guys think we should approach this one? This is the generalized pigeonhole principle. There must have, you say, David. Okay, well, and Sean says no. Okay, so what do you guys think? What are your approaches here? Okay, so if you divide 500 by 17, it's not as big as 30. Or looking at it a different way, if we said 29 times 30, 29 times 17, right? Yeah, and you can't have fractional lines, right? So you have 29 times 17. Well, that's equal to 293, as I recall. Let me double check that. 17 times 29. 493. Yes, we're doing 500, right? So we've got so 29 times 17 equals 493, right? Which means that there couldn't have been 500 lines if the programmer had written at most 29 lines per day, right? And the reason why we can't say, oh, well, maybe on one day he writes less and on another day they write more, is because if you write less lines of code on that day, you're just going to come out with a lesser number, right? We're looking at this 30 lines on like each individual day. Did the programmer write, greater than or equal to 30 lines? And so they must have, right? Because we've got this 29 here, which is the times the 17 days, which is the most they could have done if this had been false, right? So if we're trying to prove this false, this would be sort of like the worst case scenario. But in this case, it fails, right? In this scenario where they write the most lines they could on every day, less than the limit, they don't make it, right? They're off a little, right? Yeah, that was greater than or equal to, although greater than would have still been the same answer, right? Oh no, it would not have. No, if it was strictly greater than, no, then it would have been yes, actually. So Sean, if you thought that was a greater than, yeah, it would be allowed. Yep, that's true. Yep, yeah, you're right. Yeah, but greater than or equal to, yeah, we would have to have a day with at least 30 lines, and maybe more than that, depending on how those final 7 lines are distributed amongst the days, right? You could have 7 different days with 30 lines each, and the rest have 29. Or you could have, all 7 of these extra lines occurred on one day, right? So that there was 36 lines on one day and then 29 on every other day, something like that. Any questions there? Does that make sense? Okay. So let's move on. Sorry, 1 second here. Okay, great. So let's move on to section. Oh, no, there's one more. Okay. Yeah, let's do one more. So A is a set of 6 positive integers. Six positive integers, which are all less than 15. Yeah. Maybe I'll say each less than 15. Okay. Show that there must be 2 distinct subsets of A whose elements, when added up, have to give the same sum. There are 2 subsets of A where the sum of the elements are equal. Where the sums of the elements are equal. This one's a little harder. Okay, so how should we approach this one? What are the pigeons and what are the pigeonholes in this case? You can't have two pairs of elements have the same difference. I'm not sure what you mean by that, David. You can't have them have the same difference. Ooh. I'm still not quite sure what you're getting at there. 1, 5, and 14, 10. The difference would be 4 in both cases, but I'm not sure what that has to do with the question exactly. Okay, got it. Okay, no problem. So let me ask my question then one more time. So in this case, we're taking two subsets of A, and the sums of the elements are equal. Let's do an example. Maybe that'll help. So we have 6 positive integers, each less than 15. Okay, so let's say we have, 1, 2, 3, 4, 5, 6 as an example. Just a really easy one. Okay. Now what I want to show is which two subsets I can divide this into, right? Where the sums are equal, and it says two distinct subsets. Notice I said subsets, not partitions, right? So we don't have to use all of the numbers. So the worst case scenario is 1, 2, 3, 4, 5, and 14. Okay, why is that, David? Well, before we get there, what numbers could I choose here that would satisfy this question where I want two subsets where the sums of the elements are equal? Let's do this one real quick first. 6 and 4, 2. Okay, but 2, 4, and 6. Okay, what's another one? Okay, 5 and 3, 2, 4 and 3, 1. Perfect. And 3 and 1, 2 also, right? So there's a bunch of them for this one, right? You could also do 1, 2, 3, and 6. There's another option. Okay. And so let's jump back to, and Amber, yeah, you can combine multiples as well. So Amber, your idea of 3, 4, and 6, 1, that works as well. Yep, absolutely. Okay, so David, you said the worst case scenario is 1, 2, 3, 4, 5, and 14. What do you mean by that? The sum cannot be obtained. So in that case, why would the sum not be obtained there? I think the sum could be obtained in that case, as a matter of fact. Yep, 2, 3, and 5 are still subsets. That's true. You think the worst case is the most spaced out they could be. Okay, so you want like 1, 4, 7, 11, something like that. Okay. Other ideas? So Sean, I think the spacing out is a nice idea, right? But I think we want to space them out a little bit differently. What we want is we want to choose at each new choice a number that can't be obtained by adding together all the other numbers. Yeah. So really what I'm looking for is something like 1, 2, 3 can't be in there, right? So what would have to come next? Sorry, my dog is still hunting a housefly. 4, good. What would come next? Well, now we can't combine any of these guys together. So the next one would be 8, excellent. The next one would be 14. Well, I think we could make 14 with these guys, right? So I think the next one would have to be 16 if we can't combine anything together, right? So I think with 6 positive integers, then then you're definitely going to have two distinct subsets where the sums are equal, right? Because the next one would have to be 16. And we're only on the 5th element, so to speak, right? And we'd have to have even another one, right? So for this to work, you'd have to have your set of 6 positive integers be each less than 33, right? Or up to 32, and then it would still work, right? But really, the question is secretly about binary. That's one way of looking at it, anyway. What do you guys think? Does that idea of spacing make sense to you? Yep. Cool, cool. Okay, so let's move on. That's all I've got for 9.4, just a few examples of the pigeonhole principle. Let's move on to 9.5, which is all about combinations, right? So a combination from a set of n elements of, I'll say a combination of r elements from a set of n is just a subset of the elements. Okay, which is to say, if we have a set of n elements, like 1, 2, 3, 4, 5, and you wanted to know about 3 of those elements, right? You wanted a combination where you want to combine 3 of the elements from here. Well, you have some options. If you want to combine 3 elements, you could pick 1, 2, 3. You could pick 2, 3, 5. You could pick, 1, 2, 5, which is the same thing as 5, 2, 1, because these are subsets, remember, and the order in a set does not matter. So really what we're saying here, when we say subset, we're saying order doesn't matter. That's why we're saying that in there. Doesn't really have anything to do with sets at all. All that we're saying is just that the order doesn't matter. Right? So there are some different examples. This one would not be included again, because then you'd be double counting, right? Since the order doesn't matter here, 5, 2, 1 means the same thing as 1, 2, 5. So you wouldn't want to count that one again, right? And a combination is computed with choose notation. Computed by n choose r, or the notation for that is in parentheses, you put the R on top and the N on the bottom. Sorry, and choose R. Uh-oh. Is that right? Yeah, and choose R, sorry. And choose R. Sorry, I screwed it up. There we go. And choose R. Okay, so let's do some examples, right? So let's say that we want to do, we can do 5 choose 3. I don't think that's going to be too bad. So let's see if we can list out all the combinations of 3 elements that we can build from a set of 5. So how should I organize these? What do you think? Does anyone know how many there are going to be total? 5 choose 3. $20. Okay. Cool, cool. So how should we list these? This is a combination, not a permutation, because permutation, the order matters. But for combination, there's a lot less of them because the order doesn't matter. So let me get you started, right? Yeah, okay, Sean, that's you got us started. Perfect. We got 1, 2, 3, 1, 2, 4, 1, 2, 5. And then 1, 3, 4, 1, 3, 5. And how about 1, 4, 5? And those are all the ones that start with 1, right? Is everybody happy that these are all the combinations that begin with a 1? So then let's do all the ones that begin with a 2. Okay, so you've got 2, 3, 4, 2, 3, 5, and 2, 4, 5, right? And lastly, we've got 3, 4, 5. And that's it. So it's only 10. Yeah, not 20. You were so when we start talking about Pascal's triangle in a minute here, you were off by 1 row. 6 choose 3 will give you 20, but 5 choose 3 gives you 10. Cool. Okay. So there's a little example, but there's a nicer way of doing this because you don't want to have to list these out every time. And I think we've talked about this before, but let me repeat it. This choose notation, let me get rid of my period here. There's a formula for it. Does anyone know the formula? Okay, so the formula is n factorial divided by n minus r quantity factorial times r factorial. Okay, now let's do that here and see what we get, right? So here we'll have 5 factorial divided by 5 minus 3 is 2 factorial times r, which is 3 factorial. So what is this going to be? We'll have 5, 4, 3, 2, 1 divided by 2 times 3 times 2. Well, the 3's cancel, the 2's cancel. The 2 cancels one of the 2's inside the 4, and what do I have left? 5 times 2 equals 10. It works. What do you guys think? Questions so far? Okay, so let's do a couple of weird examples, just to be clear. For any n, what's n choose n? If you have n items and you pick all n of them, there's one way of doing it. How about n choose 0? I choose none of the items. Also equal to 1. There's only one way. Think of it as you're picking a soccer team, okay? There's only one way of choosing everyone to be on your team. There's only one way of choosing no one to be on your team, right? Okay. What about this? What if I have n choose -4? What would that be? How many ways? No, it is defined. How many ways are there? Yeah, 0 ways to choose -4 items out of a set. That's it. It is defined, but it is not possible to find one, right? So impossible rather than undefined. Slight difference, right? Okay, so that is also the true for anything bigger than n. So if we have n and then n plus 3 or something, right? There's no way to have n items and pick more than n items out of it, right? You only have n choices, so how can you pick more than what you have available? That also, there's no way of doing that. People happy with those little goofy examples? Any questions? Okay, so let's try another one here. There's 12 students in PE class playing basketball. How many teams can be chosen? And a basketball team has 5 people on it, right? Just one 5-person team. Yeah, they're playing they're playing the fourth and the fourth graders are playing the fifth graders, and we got 12 fourth graders. We're wondering how many different teams we could make. So just one team. Okay, good. So we've got 12 choose 5, which, as you correctly said, Sean, is 12 factorial divided by 7 factorial times 5 factorial. And let's write it out, right? So the easier way to do this is take the bigger of these two numbers, and that's where you'll start writing the numbers up top. Or maybe that's where you'll stop writing the numbers up top. Let's do them in reverse order. So I'm going to have 12, 11, 10, 9, 8. That's what remains when we cancel off the 7 factorial. And that whole thing's going to be divided by the 5 factorial. 5, 4, 3, 2, 1. Right? So what we can do now is say, okay, well, the 10, that's equal to 5 times 2, so we'll cancel those. 12, that's equal to 4 times 3. What I've got left is 11 times 9 times 8. 99 times 8, that gives us 792. Right? So there's 792 different basketball teams that could be chosen from 12 students, which is a lot. These numbers grow pretty quickly. We're actually going to study how they grow. As you increase the top number or the bottom number, the total that you get changes, right? Obviously. But how it grows as these numbers grow is an interesting question that you can analyze in a variety of different ways because of the relationship between choose notation and Pascal's triangle, which hopefully we'll get to today. I very much hope so because it's on your midterm. So So let's keep moving. Okay. Do another example here. Did anyone have any questions on that one before we go on? People happy with this? Okay. So we have the same setup, 12 students. We're picking 5 people for the basketball team. Okay. So 5 people, 12 people, choose 5. But in this question, 2 members of the group insist on working as a pair, right? But there's 2 BFFs, right? So these kids, they're best friends. They say, hey, you know, either we're both on the team or neither of us is going to be, right? Is everybody following? Which are both chosen or neither? Okay, so how would I approach this question? Good, and what would the 2 cases be? Right, they're either on the team or they're not. So either on or off the team, okay? If they're on the team, how can we count up now how many different combinations there are for the team? Close. You are choosing 3, but it's not 12 choose 3. It's what? Yeah, 10 choose 3. Good, because the 2 people were already on the team, so there's only 10 remaining people to be chosen. Right? Okay, how about then if they're off the team? So if they're off the team, so then Brian, yours comes into play. Yeah, 10 choose 5. That's right, Sean. Because if they're off the team, then there are 10 other people to pick from, and we're picking 5 of them, right? And since you can either be on or off, how do I combine these things? What's my or operator here? Add, good. So we add the ways that they could be on and the ways that they could be off. So we'll add these together and we'll get, I don't know. Sure, I don't want to compute this, but it's 372. This one is 120. This one is 252. Gives us 372. Okay, so let's try another way. Now, instead of saying there's 2 BFFs, same, but 2 enemies. Right, so instead of having 2 BFFs that have to be on the team, there are 2 kids that hate each other. And if one of them is on the team, then the other one refuses to play, right? And same vice versa, right? So now what do we do? Two times 11 choose 5. Close. It's 2 times something. And it's not 11 choose 5 though, but you're on the right track. Closer. Closer. We're getting there. 10 choose 4. Okay, why is it 10 choose 4? Okay, you fill the spot with 1 enemy and 10 people remain, and you're choosing 4 of them because you already filled one of the 5 spots. So one of the 5 spots is filled with one of the enemies, right? Which leaves 4 spots remaining. And from that, there's only 10 people left to pick from because one's on the team already and another's an enemy. So there's 10 people left. Okay, we're almost there, but not quite. What else might happen? Good. We could pick neither of them. Say you guys are poor sports. We're not going to pick either of you, right? So what would that be? So, or we pick neither of them, which would be 10 choose 5. Perfect. Everybody good on that? Excellent. So this would be 2 times, what have I got here? 210 plus, again, 252 equals 672. Right? So it turns out there's more ways to make teams if there are 2 enemies, almost twice as many, or more, almost twice as many ways to make teams with 2 enemies rather than teams with 2 friends. And so enemies don't restrict your choices as much as friends do, right? Which is interesting. Any questions there? Makes sense. Okay. Okay, so their next question is about types. And I'm just running through the chapter examples here, right? So we've got 5 men and 7 women. Maybe this is a kickball team. Okay. And we're picking 5, or sorry, well, no, this is still basketball because we're picking 5-person teams. Still 5-person teams. Okay, so here's the first question. How many teams with 3 men and 2 women? Okay, so in this case, there have to be exactly 3 men and exactly 2 women. Yep, so it'd be 5 total men, and from the total men, you pick 3 of them. And, which is multiply, you have 7 women, choose 2 of them. Right? Any questions there? People starting to get the hang of this? Yep, okay, good. Let's try another one. So let's say, how many 5-person teams have at least 1 man? So how many teams with at least 1 man? 12, choose 5 minus 7. Oh, okay. Well, that's different than how I was thinking about it. What's your thought process there, David? Ah, okay. The 12 choose 5 total combinations, and then the 7 choose 5 would be the all women team, right? So if you take the total minus the all women, which would be 7 choose 5, right? 7 women, we choose all 5 of them for the team, right? Get rid of those, and for all the rest of them, there'll be at least one man. That's one way of thinking about it. Awesome. 12 choose 5 minus 7 choose 5. Okay. What's another way of thinking about it? Okay, so another way of thinking about this is that instead of removing the all women's team, the all women's team, instead you add up all of the different combinations of men's teams with different amounts of men on the team, right? So you would say, okay, well, I could have one man on the team, or 2, or 3, or 4, or 5, right? So one man would be 5 choose 1, and, right, times the choices of women. So Tamara, you had the right idea for the men, but you have to, for each one, multiply by the women chosen as well, right? So here you've chosen one man. Okay, good, you got it. So how many women would we be choosing for this first one? Perfect. 7 choose 4. Awesome. Right, so that's for one man. Or we could pick 2 men out of the 5 and 3 women out of the 7. Or we could pick 3 men out of the 5 and 2 women out of the 7. Or, and I think you get the idea, right? 5 choose 4 times 7 choose 1. 5 choose 5 times 7 choose 0. And you might wonder if these things are equal. That's something I suppose we could check, but they are. I'll just tell you that right now. Right? You're welcome to check on your own. Okay. So let's do one more. How about at most one man? So how would we analyze that one? Okay, so let me give you a hint. Okay, good. 1 man, 4 women, plus no men, 5 women. Perfect. Okay, that's great. So let's fill those in. So if we have 1 man and 4 women, what will my choices be? Okay, 5 choose 1. 5 men choose 1 man times 7 women choose 4 of them. Or teams with no men and 5 women. 5 choose 0 times 7 choose 5. And since 5 choose 0 equals 1, and we're multiplying by 1, we can actually skip that 1 and just say 7 choose 5. Little shortcut. What do you guys think? It's good? Makes sense. Awesome. All right, moving right along. We could do poker stuff. Let's skip over the poker stuff. That's okay. We're going to keep rocking and rolling here. How many bytes have exactly 3 ones? Remember, a byte is an 8-bit string. Oh, the midterm practice with choose notation. Sure. Was that last problem that I was talking about, David? Number 5, is that right? Yeah, okay. Yeah, let's do that one after this one. Yeah, great. That'd be perfect. Okay. Yeah, of course. Thanks for reminding me. Okay, so what do you guys think? How many 8-bit strings have 3 ones in them? Well, how should we think about this problem? What are we choosing in this case? Well, we are choosing between 0s and 1s in a certain sense, but I think that's not the easiest way to think about it. How else could we think about what we're choosing? And David, you can do it that way, but there's an easier way of thinking about it. Yeah, the positions, that's right. So if you think about it in terms of slots, there's 8 slots, and we have to pick where we put the 3 ones, maybe here, here, and here, right? Where? Right, where do we put those ones, right? And so, how many total choices will there be? Perfect, 8 choose 3. 8 choose 3, right? Because we have 8 positions, we're choosing which of those 3 have the ones in them, right? Questions? Okay, so let's pop back over to our sample test here, practice test. And we want to show that the subsets of A whose size is even subsets of even size equal, I guess I should say the number of subsets of even size equals the number of subsets of odd size, right? And let's say that our set A, the size of it equals n, right? Just to give ourselves a variable name to work with here, right? Okay. So now that we're thinking about choice, what's going to happen here? How can I think about the subsets of even size? You could think of it total minus odd equals even. Yeah, you could think of it that way. So what's our total then? Yeah, what's our total going to be if we want to think about the total number of subsets and include that idea, which is fine? How many of those would there be? Two to the n. Good, because we're thinking about the total number of subsets, which is this the size of the power set of A, right? The size of the power set of A, of course, is equal to 2 to the n. That's our total, right? So if the subsets of even size are equal to the subsets of odd size, what would we want to show? How big would the subsets of even size need to be? We could actually, at this point, we can kind of forget about the subsets of odd size, so long as we find what? Yeah, we would get 2 to the n minus 1, right? The number of subsets of even size be 2 to the n minus 1, and then 2 to the n minus 1 over here. It would have to split it in half if they're equal, right? Okay, so now what we've gotten to is to say, okay, well, and this was not the direction I was going to go, but that's fine. So now we want to show that the subsets of even size, when we add them all up, right, is going to be 2 to the n minus 1. Okay, so how should we think about that? What would be the subsets of even size if we tried to list them out and add them up using choose notation? What would that look like? And again, feel free to hop on the mic here if it would take a while to type that out. Ideas? What would be an example of one kind of subset of even size? Let me ask that question better. What's the smallest even size subset you could have? Empty. The empty set would be the smallest even size subset because its size is 0, which is an even number, right? Now to represent that with choose notation, we'd say, okay, well, we're going to take n, and how many of the subsets are we going to pick? And choose what? Not n over 2, not quite. Okay, so let me, yeah, for empty. So yes, let me say the question one more time. So I'm talking about how many empty sets are there going to be, right? Which would be n choose 0, because 0 elements go in the empty set. And of course, there's one of them. N choose 0 equals 1, because there's one empty set that we could make. Or what's the next biggest size of subset we could make? N choose 2. Beautiful. Or what's next? N choose 4. Perfect. And now you get the idea. N choose 4, right? Dot, 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 up to what's the last one going to look like? Well, it might be n choose n minus 1. It depends on n, that's right. Because what if n is even versus n is odd, right? If n is even, then the last one will be n choose n minus 1. But if n is odd, then we'll start at 0. We'll go 0. So if n is odd, right, that's going to be the number of items in the set. So we could have, 0, 1, 2, 3, 4, or 5, for example. Right? So n is odd, which is 5. And here we're going to pick out n choose 0, n choose 2, and n choose 4, right? And then this last one won't be included. So these ones would be the evens, and these one would be the odds on top, right? So it might come up to n minus 1, but what if we had an even n? What if we did 0, 1, 2, 3, 4? Well, in that case, the evens would be all the way up to n choose n, right? Because 4 choose 4 would be the last one. So it does depend on the parity of n, right? Okay. Well, let's do this. Let's think about this particular case because it's pretty, right? The other one is interesting, and I'll leave it for you to think about. But here, this one is going to give us a really sort of elegant result. Let me show you why. Rather than just writing out the even ones, let me write out all of them, right? Let's write out, 5 choose 0, 5 choose 1, yada, yada, yada down the line. So I've got, let me make some space here. So I've got 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. Okay. And let's write out the numerical value for all of these. So we know that anything choose 0 equals what? 1. We know that anything choose itself equals 1. We also know anything choose 1. Here's another little fun example. If you have 5 items and you pick one of them, how many ways are there of doing that? 5. What if you have 5 items and you pick 4, which is excluding 1? How many of those would there be? Also 5, right? What about 5 choose 2? Well, we can use our little formula for that. Yeah, those are 10, right? So you can say 5 choose 2 is, and it's going to be Pascal's triangle. So 5 choose 2 is 5 factorial divided by 2 factorial times 3 factorial, which of course is, we delete the 2, the 3, and part of the 4. So we get that's 10, which of course is also equal to 5 factorial divided by 3 factorial times 2 factorial, which of course is 5 choose 3, right? Because here you have, oh, I did it backward. Here's 5 choose 3, here's 5 choose 2. But this is n minus r and r. This is n minus r and r. But either way, it's going to be 10. And what we're going to get is a row inside of Pascal's triangle, it turns out, which we're going to talk about why that is in just a minute, right? So think about what we're picking here, right? Here's the evens. We got a 1, a 10, and a 5, which are length 0, 2, and 4, the even numbers here. Here, we also have a 1, a 10, and a 5 going in the other direction. So here, for the evens, we have 1 plus 10 plus 5, 1, 10, and 5. And we want to know, is that equal to 5, 10, 1? Or if we read it in reverse order, 1 plus 10 plus 5. And yes, it certainly is. They're both equal to 16, which you'll notice is 2 to the n minus 1. Here's 2 to the n if you add up everything in the row. 10 plus 10 is 20, 32. If I plus add all of those together, it equals 32, which means if we take each side and cut it in half, we'll come out with 16 on each side, which it turns out is the case. What do you guys think? Happy so far? Yes, okay, cool. So let's talk about why, these things have to be equal, right? Well, you can kind of see it here, right? Because we're adding 1 to the evens here, which means we have to add 1 to the odds on the other side. We add 5 to the evens, 5 to the odds here, which means we add 5 to the evens on the other side, and then we switch 10 to the evens, 10 to the odds, and now we're done, right? And since we sort of moved in this direction, right, you can see that because Pascal's triangle is symmetrical, the number of even subsets must equal the number of odds, because you just flip the thing over and reverse which number pairs with the evens and which number pairs with the odds, which means they have to equal each other. Yeah, here we have up, down, up. Here we have down, up, down. So you just switch which number pairs with which group, which means you'll have to get out the exact same number since the triangle is symmetrical when you flip it. Questions? Okay, so yeah, so we can think about it the other way. What if we have 1, 4, 6, 4, 1? Okay, so here we have the evens here, 1, 6, 1, and the odds here. And of course, you will see that 8 equals 8. But it doesn't have that kind of pretty pattern to it, right? Where we not only do the numbers not match, right? We have 1 plus 6 plus 1 equals 4 plus 4. So not only do the numbers not match, there's not even the same number of elements that we're adding up here. So this sort of row of the triangle doesn't lead to as an elegant of a solution as this one does, which is fine, right? If you were proving this, you would have to show it for both, right? Or show it that, you know, if you do it for one, you could do it for the previous one or something like that. So you could do like a partial induction proof. But, you know, if you wanted to show that this was always true, you'd have to show it for both kinds of rows, the kind of row that has an even number of entries and the kind of row that has an odd number of entries, which will pop out differently, right? Now, if I wanted to write this down formally, what I would say, let's do it for this one. I would want to say that the sum, maybe I should go to a new page here. I'm going to say that on this side, let me start with this one. The sum from I equals 0 to n over 2 of n choose I, 2 times I is equal to the sum from I equals 1. Oh, crap, I screwed this up. The even should be from 0 to n. No, I did it right. From 0 to n over 2. This will be from 1 to n over 2 quantity minus 1 of n times n choose 2I minus 1. Why is that? Let's think about this sum for a second here. Well, maybe let's do the easier one first. Okay, I is going from 0 up to n minus 2, 0 up to n over 2. So here's my counts of n. We got 0, 1, 2, 3, 4, right? So what's happening with this I? Well, I goes 0, 1, 2. And when we're doing our choices, we have 0, 1, and 2, which gives us 0, 2, and 4 when we multiply by 2 inside of here. So we're picking out 0, 2, and 4. That would be this kind of a one here. This would be the 1 and the 3. How do we pick that out? Well, we'll start at 1, I equals 1, right? And we'll say, okay, 2 times 1 minus 1 equals 1. But what happens next? Now we move on to 2. And we have 2 times 2 minus 1 gives me 3. And we stop at 2 because n over 2 in this case would be 2 minus 1. Oh, yep, I don't think I need this. I'll take it back. I thought I was being clever, but I was actually wrong. This still goes up to n over 2, right? Because we would go 1 and then 2, and for 2 we would have 4 minus 1 is 3. Yep, okay. So here's how you would write this formally. Proving this is a different kind of deal, right? So you would have to have some facility, some tools that you could use for summations of choose notation. Now we're going to get some of those tools hopefully today. But since you don't have any yet, I think this kind of an argument would be something more appropriate to the practice midterm had you not been able to resolve the closed form for sums like these, right? Because if you get to this point in your proof and you're like, well, now I don't know how to compute this, well, then, then that's not a very good proof, right? Is everybody with me there? If we were to look at this on the other side, right, here, I could think of it this way. I'm going to add up, I'm still going to be adding up this same sum, the sum from I equals 0 to n over 2 of n to the 2 times I, right? That'll be for the even ones. But for the odd ones, what I'm going to do is something a little different. I'm going to add them up, but going in the other direction. So here, I'm going to have the sum from I equals n, right, down to, so I'll be going in the reverse direction, down to I equals 0, I equals 1. And I'll have the same thing here. Oh, sorry, starting at n over 2, pardon me. Have the same thing in here, n 2 times I. Wait a minute, one moment. Right, yeah, that's right. Okay, just had to think for a second there. And what, at this point, and David, I'll get to your question in just a second. At this point, what's happening is you have this sort of situation where on this side of the summation, you have n choose 0 plus n choose 2 plus n choose 4. And on this side of the sum, you have, first of all, n choose n, which I guess would be 5, right? Then n choose 3, and then n choose 1. And how would you know these things are equal? Any thoughts on that? I guess all of these n should be 5 in this particular case. Any thoughts there? See a principle of a pattern in this row that we could use? Yeah, good. These guys, 5 choose 5 and 5 choose 0, these are the same. Also, these guys are the same. Also, these guys are the same. All the numbers are actually equal to each other. So this proof would be a little easier than this one, because here you're adding up all these weird numbers. Here's a way of expressing that. Here, we're adding up the same numbers, so of course they're going to be equal to each other, right? Okay. Let's do this. I need to take a short break, so let's take 5, and then we'll come back and try to finish up the binomial theorem and maybe some questions out of 6.5. So we'll be back in 5 minutes. See you soon. All right, so the last couple of proofs I want to do come from 5.7, and they really explore why the choose notation it lives inside of Pascal's triangle. Okay, why is it that when we do this choose notation, we get the numbers inside of Pascal's triangle, right? So we can do this a couple of different ways, right? What we're going to try to show is that n plus 1 choose r equals n choose r minus 1 plus n choose r. Okay. Why are we proving that? Thoughts? Okay, so I'm gonna pause less because I do want to finish these up in the next 20 minutes. So the reason why we want to prove this is because this is the rule for Pascal's triangle. Let me show you what I mean. Let's build Pascal's triangle out to 5 places. So I have 0, 1, 2, 3, 4, 5. And I'm going to make a right-handed, a right-angled Pascal's triangle rather than a centered Pascal's triangle. Let me show you what I mean. It'll just be easier to index the elements that way. So here's Pascal's triangle: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and 1, 5, 10, 10, 5, 1. Okay, and we can think of this as like a, grid here. Right? There we go. Okay. Now, usually this thing isn't a right triangle like this. Usually it's kind of centered, right? But certainly we can think of it this way, right? Where instead of the usual rule for Pascal's triangle, which is you take the 2 diagonal numbers on top and add them to get the number below. So for example, 1 plus 3 gives us a 3, 3 plus 3 gives us a 6, 3 plus 1 gives us a 4. And there are ones on the outside because the whole thing is surrounded in a big ocean of zeros. Okay. That's the usual rule for Pascal's triangle. You take the 2 elements above, add them to get the number down below. Right? And here, instead of taking the 2 elements above, we take the element above and the element above and to the left and add those together to get out our answer down below. So above and to the left, right? Well, what is that? 3 plus 3 equals 6. The one above and the one above and to the left added gets us a 6. What does that have to do with our formula here? You look to the row above. Good. So the rows in this case are going to be n. The columns are going to be r. Right? So what happens if we're looking for example, 4 choose 2, well, what is that going to be equal to? Well, if 4 is n plus 1, then n has to be 3. So we'll have 3 choose 1 plus 3 choose 2. And what's that saying? Well, if I go to n4 r2, which is 6, that equals n3 r1, that's our 3, and then n3 r2, that's our other 3, right? So this is really just a way of indexing using choose notation, right? To get us that same rule that generates Pascal's triangle, which is, well, hey, add the item above and the item above and to the right. This is the item above. I'm sorry, I said above and the item to the left is what I meant. This is the item that's above, and this is the item that's above and left. Right? We're going to add those to get our next result, right? So if I could prove this, which I'm going to do in just a second, right? Then you could see that, well, okay, well, once I know this, then the pattern encoded by choose notation is the same as the pattern that's encoded by Pascal's triangle, which is why they generate the same numbers. What do you guys think? Are people with me so far? Questions? Makes sense. Okay. So let's do a proof, right? So here's our proof. And we're going to do this 2 different ways, okay? So first of all, we can do it algebraically. And we can say, okay, well, I've got this guy here. Let's see what happens when I add these things together, right? So I'll have n choose r minus 1. Well, maybe I'll just write it out. So that'll be n factorial divided by what? N factorial divided by n minus r plus 1, because that's a minus factorial, times r factorial, which would be, in this case, r minus 1, quantity factorial, plus, here I have another n factorial on top. And on the bottom, now I have r's, so I have n minus r factorial and r factorial. This is actually the second time we've done this proof. I believe we did it last term as well, right? So once I have this, what should I do next? Anyone see algebraically how to combine these 2 guys? So if we're adding fractions, what's our move here? Good, common denominator. And so what our common denominator is going to be is n minus r plus 1, because that's the bigger of the 2 numbers on the left, and r on the right. Okay, so my common denominator is going to be n minus r. Oh, wait, is that right? Sorry, 1 second. Yeah, n minus r plus 1. And r from the right. And now what's going to be on top? Well, now we need to multiply each of these guys. Yep, n factorial. And I'm just going to factor that out. I'm just going to factor out an n factorial. What's my, what am I missing over here? Well, from this guy, I'm missing a factor of r. And on the right side, I'm missing a factor of n minus r plus 1. Then simplifying, what do I get? Well, I've got what do I have here? I've got r minus r, so these guys cancel, right? I've got an n and a 1, so I have n factorial times n plus 1. And what do I have on the bottom? Well, on the bottom, I have n minus r plus 1, which is equal to what? Well, that needs a little trick, right? Here's the little trick. N plus 1 minus r, quantity factorial, times r factorial, which of course equals n plus 1 quantity factorial on top, because we have all the 1, 2, 3, 4, 5 up to n already. We multiply by n plus 1, that just brings us to n plus 1 factorial. So the whole thing is just n plus 1, choose r. People see it? Any questions? Any questions on the algebra here? Looks good. I think that the tricky part here is seeing to put this plus 1 over onto the n, so that when we have, our definition of choose notation, which is n minus r, here for our n, we have an n plus 1, which is our top guy, right? It's the top guy minus the bottom guy factorial. So there's the top guy, right, minus the bottom guy factorial times the bottom guy factorial, right? Okay, so there's another way of thinking about this, which is combinatorial. So let's say that we have n plus 1 elements. So here's proof 2. Here's proof combinatorial, comb. Okay, say we have n plus, we have a set of n plus 1 elements. Okay. Now the subsets of size r can be thought of in 2 parts. We could think of them as being the subsets with the n plus first element and the other without. Let's think of how many of those there would be, right? So if it does contain the n plus first element, right, then it's going to be okay, if we do have the n plus first element, there would be n choose r minus 1 of these, because we would have 10, sorry, not 10, n elements total, but one of them we don't get to pick anymore because we already have the n plus first one there. The one without the n plus first element, well, that would just be n choose r. Add those, get our answer. What do you guys think? Maybe you like this proof better? questions? You do personally. Fair enough. I do too. I think it's a lot more elegant. Yeah, let's do it one more time. Okay, so we have a set of n+1 elements. So we have a set of n elements and we want to add on a new one, the n plus first one, right? Once we add that on and take subsets, there are two categories of subsets. The ones that do have the new element, in which case from n choices of the original n, we already have the n plus first one. So from the original n, we can only take r minus one of them because one of those slots was taken by the n plus first element, right? Or for a subset without the n plus first element, that means from the original n, we can't choose the n plus first one now. So just from the original n, but this time we get to pick all r of them. Is that better? You got it. Nice. Cool. Okay. So this is the algebraic proof, and here's the combinatorial proof. Fair enough. Let's do, and what should we do last here? Let's talk about the combinatorial proof of the binomial theorem, because we have to do the binomial theorem. So let's make sure I get one of those in. Here's the binomial theorem. The coefficients of a binomial expansion can be found with choose notation, can be computed. Okay, so first of all, let's talk about what is a binomial expansion, right? So a binomial expansion is something of the form x plus y to the n, right? And let's do an example. So let's say we have x plus y squared, right? X plus y squared, what are we going to get? Perfect. X squared plus 2xy plus y squared. Right? 1, which is not there, but it's implied, right? 1, 2, and then another implied 1, which is the row from the triangle. X plus y cubed is going to be x cubed plus 3x squared y plus 3xy squared plus y cubed. The powers of the x are decreasing in each term. The powers of y are increasing in each term. And what I want to show is a combinatorial argument as to why I could think about this as 3 choose 0, x cubed, 3 choose 1, x squared y, 3 choose 2, xy squared, and 3 choose 3, y cubed. How come these coefficients come from the triangle, right? And the way to think about that is the different combinations that we can make of x's and y's. How many can we make? Well, here we're taking 3 x's and putting them together. So we have out of 3, it's all x's. There's no zeros, right? But on the next one here, 3 choose 1, here we have 2 x's, but we're picking 1 y. And really the question is, when we think about x plus y cubed, looks like this, and we think about these terms that we're going to make, right? We could have an x cubed term, right, where we pick x, 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 right? That'd be our x cubed. But when we do x squared y, what are we choosing? Well, we're choosing which of the three factors, which of the three terms in the expansion the y comes from, right? It could come from this one, or this one, or this one, when we FOIL and multiply everything together, right? Same deal for 3 choose 2. Here we're choosing 2 of the y's, right? So we pick either these two, or these two, or these two, right? And 3 choose 3, well, there you have it, right? Let's do a little bit more interesting example, right? Let's say that we want to choose, we want to think about x plus y to the 4th. Well, I'll just throw one more on here, save some time, okay? And let's say we want to know the coefficient on the x squared y squared term. Well, how would that look? Well, we could have the, in our expansion, we could have, what would we have? Well, we could have x, x, y, y, right? We could have x, y, x, y. We could have y, x, y, y, x. We could have y, x, y, x, y, x, x, y, or y, y, x, x. And those are the 6 different combinations that you can get if you choose the y's from these two, these two, these two, these two, or these two, or these two, right? 6 of them. A little bit like a cross product, yeah, a little bit similar, right? So as you FOIL this out, you're picking x's and y's from each of these different terms to combine. And the question is, well, how many ways can you pick 2 x's and 2 y's? Well, 4, choose 2 y's, right? And so that's why the coefficients in that's why the coefficients of a binomial expansion can be represented using choose notation. And that's why you can use Pascal's triangle to easily unfold one of these binomial expansions, so long as you have the rows memorized, right? So that's all I've got for you for today. I would highly recommend going through your book and reading up on that binomial theorem, because that's the main focus of section 9.7. And then you should be in good shape for your midterm. Your midterm is not going to have 9.6 on there. I did not get to that today. I believe there is a web work section on it, as I recall. Let me double check that. I think there is. Is there a 9.2? I'm logged out. 1 second. There's not a 9.6. Okay, so we're skipping 9.6. No big deal, right? So if anyone has questions on 9.6, feel free to fire them at me. Yeah, I'm not going to do an extra lecture. Yeah, I don't have time this week. So we're just going to skip 9.6. It's not going to be on your midterm, and there's not even a web work on it either. So we're just going to skip it. Yeah. If anyone wants to go through and do some practice problems out of there, that's great. I'm happy to, during office hours or even during lecture next week, talk about any issues you had on the practice problems there. If you want to go do some exploration, that's totally great. Happy to go through it if people would like to next week. Okay. Does anyone have any questions for me before we go? Thanks so much, Tamara. I appreciate that. Yeah, I'm sure by Monday I'll be in ship shape. I'm feeling better already. So. Yeah. Anything else before we go? Any questions about the midterm, how that's going to work? That's probably the most important thing. Anything else? Starts on Saturday night, so Sunday morning. Everything up to 9.7 except for 9.6, which we're skipping, and we didn't do sections 8.4 and 8.5, so those will just not be included either. Cool. All right. Well, have a great one, everybody. Thanks so much, Dad. Appreciate that. And I will see you all on Monday, where I'm sure since we're doing the timed version, I guess we won't have questions at that point, but that's fine. On Wednesday, we'll go over the midterm and we'll talk about all of your answers. All right. Well, have a great weekend. Good luck studying and good luck with the practice exam. Thanks, Kobe. Yeah. Have a good one, everybody. I'll see you next week. Bye, guys.